Okay, hello everyone. Today we are moved to chapter 8. The topic is the dimensional analysis and the similitude. So, actually, in next semester, we will have a serious laboratory experiments, and usually we apply the laboratory experiments to predict and understand what the practical behavior for some phenomena. But before that, we need to conduct a serious dimensional analysis and try to use the dimensional analysis to understand the physical behavior in true environment. And then we need to consider that uh, the model and the prototype. Uh, how can we use the model to predict the prototype behaviors? So there are three uh, uh, similitude we need to satisfy before. The first is the geometric, the second is the kinematic, the final is the dynamics. So if we would like to predict uh, the practical physical behaviors by the models, we need to satisfy the some similitude analysis. So the photo showing here, which is the models of a Formula racing car that was built out of clay for testing in the small uh, wind tunnels. The purpose of the testing was to assess the jack characteristics. So we just we can take a look the movies showing here.
At first glance, this may seem like a group of adults building a model airplane, but this is no toy.
We're conducting a wind tunnel test of the Boeing 737 MAX.
The 737 MAX is Boeing's latest design in the 737 family. It will deliver significant fuel savings over today's main competitors. And a big component of getting that efficiency is the new advanced technology winglet.
Along with the upper winglet, we've added a lower winglet. The lower winglet, in addition, moves the effective span of the wing outboard, reducing drag and improving the fuel burn for the customers.
And helping to prove the new winglet's ability to create those improvements is done here, at Boeing's Transonic Wind Tunnel Testing Lab. This is where an exact scale replica of the MAX is put through a battery of tests, mimicking flight at cruising speed. From perfect dimensions.
You saw these guys check the model, and the slightest roughness in the wrong place, they'll have it fixed and make sure it's exact.
To pinpoint measurements.
If you got out of the shower and your hair wasn't dry and you stood on a scale, we can measure your weight change as your hair dries. I mean, we're in extreme precision.
This lab makes for the most accurate results possible. And in this case, those results came back just as predicted.
In the end of our wind tunnel testing, it validated that the aerodynamic improvements coupled with the engine improvement will deliver at least a 13% improvement over the existing next generation airplane.
And these results are not only validation, but another sign that the MAX is well on its way to becoming a staple in commercial aviation.
It puts us in a great position to firm up our configuration by mid-13, which will allow us to design it in 14, build it in 15, fly it in 16, and deliver it in 17.
Okay, so the video just shows the testing for Boeing 737. As you can see, they just are testing the models under different airspeed and to see what happens, such as they try to testing the behavior of the adding flow of airplanes. So actually, we cannot build up the true airplane and then to see what happens. But we can conduct a serious laboratory testings and we adjust the different airspeed and to see what happens on the airplanes. And after that, we can, based on the result of the model testings, and to uh, predict the truly physical behaviors of the airplanes. So, but we cannot directly to conduct model testing. Before the testing, we need to satisfy some similitude between the models and the true conditions. So there are the learning outcomes. So the first we will provide a brief introduction of the dimensional analysis. And then there are two methods to do the dimensional analysis. The first one is a step-by-step method. The second one is the exponent methods. And what is the common pi groups? And we just provide certain definitions of the pi groups and explain each pi groups and related to their physical phenomena. And as I mentioned, most important things in these chapters, if we would like to predict the physical phenomena in real case by model testing, we need to satisfy the geometric, kinematic, and the dynamic similitude. So why need for the model testing? As we know, some physical phenomena it is very difficult to observe in real case. For example, the turbulence and the separating flows actually is very difficult to capture in real case. So we need to conduct the model testing to predict the true phenomena uh, and true behaviors in real case. And the basic ideas, we need to satisfy the scalings for the models to the real case. And because the model testing can repeatedly conduct, so that will be one of the advantage of the model testing because the cost of the model testing is low, so that we will have the advantage to repeatedly conduct the model testings. Okay, so as a provide the summarize, so based on the scaling and ideas, so we can conduct the laboratory experiments, and because the small size and the low uh, price for the laboratory experiment, so we can conduct a series model testings repeatedly. So this is one of the examples that explain why we need for the dimensional analysis. So as you can see, this is our the free balls velocities, and we have the diameters d1, and we have the small diameter d zeros, and this is the pressure one for the free field, through flow field, and this is uh, the pressure two in the small diameters regions. So we just make one plot. We know that actually the pressure difference when we conduct the laboratory experiments, and we have the velocities. So the figure showing here, you know that the different diameters conditions, we will have a different relationship between the pressure difference and the velocity of the free flow. But we do some rearrange of our x and y values. As you see, we just the x-axis change to the ratio of the diameters is the d0 divided the d1s, and we just compute the ratios between the pressure difference and the kinematic energies. And you see that even though we change the different small diameters, but we can see the always they are following the same relationship between the ratio diameters and the ratio of the pressure difference and the kinematic energies. So we actually know that the pressure difference divided the kinematic energy ratios is a function of the diameter ratio here. Okay, so this is a difference coefficient. We call that the pressure coefficient. Okay, the pressure coefficients, and this the D0 and the D1 is the diameter ratios. So for this experiment, for any specific orifice designs, and the pressure drops, divided the kinematic energies for the model is always the same for the prototype. Okay, so and then you see there is no any dimensional, and there is also no any dimensional. The this is uh, dimensionless parameters. So if we conduct the dimensional analysis and try to do some dimensionless parameters, and then we can see the simple relationship between two dimensionless parameters. But before that, if we don't conduct a dimensional analysis, try to remove the dimension uh, for each parameters, we cannot see the simple relationship between two parameters. In the different diameter condition, we will have a different relationship. So it's very difficult to better understand uh, the physical behaviors. So before we do the dimensional analysis, we need to know how many dimensionless parameters will be have in our prototype. So for example, we consider jack force, and we know that the jack force will is now to be a function of the velocity and the density and the viscosity and also the pipe diameters d. So we can count how many variables for our physical problems such as the jack force. So the 1, 2, 3, 4, 5. So totally we have the 5 variables, right, for our physical problems. And how many dimensional are involved? As you see, what are the force? The dimension of the force is we need to have the mass first, and the force is equal to the length divided the time squared. And what is the velocity? The velocity dimension is the L divided T. And the density, we know that the density is the dimensional is the mass divided the L cubed. And the viscosity dimension. The viscosity, if we remember, the viscosity can compute it uh, uh, from the tau is the shear force, and we have the viscosity here, and we need to know the velocity gradient. Okay, so we know that the tau is the shear stress, so the dimensional of the tau is the force divided the areas, right? And then we know that the force, the dimension is the m L t squared, and divided the area is the L square over 1. Okay, so the dimensional is the m divided the t squared and the L. And the right hand side, the dimensional of the velocity gradient here. Okay, so we know that the dimensional of the velocity gradient, so the velocity is the L divided the d. This is the velocity, and we divided the dy, so it's L over 1. So the dimension for the velocity gradient is only the t over 1. So we actually know that the dimension of the viscosity is the m divided t divided L. Okay, and the diameters of the dimension is only the L. So we just count how many dimensions are involved. We have the m mass, and we have the L length, and we have the time t. So totally we only have 3 dimensions for our problems. So there are the 2 pi groups for our problem. The 2 is equal to the 5 minus the 3 in involved in our problems. So this is very important. We call that the Buckingham's the price theories. So we need to consider since we pick up the one physical parameters. So the slide showing here is the drag force, and we just list all of the physical variables will be applied and mentioned in our drag force. And we just list all of the physical parameters and to see what are the basic dimensions are involved in for our problems, and then we just take the total variables minus the basic dimensions numbers, and then we will result have a result for the how many pi groups involved. So the table just lists all of the, the dimensionals, and so we have a length, speed, mass, density, force, and the pressures. So we see that we use the L and the M indicate the mass, and we have the T indicate the time. And in that way, the temperature we will use theta. Okay, you can take a quick look. And right now, we just introduced the first one, methods to do the dimensional analysis, which is the step-by-step methods. So the table just lists the steps for the step-by-step approach. So I just list and for the quickly provided the brief introductions. So first, we just list all of the physical variables, and then we list all of the dimensions for our variables. And usually we will use the density to cancel out the mass dimensions for other parameters, and we will use the velocity to cancel the time dimension for other parameters, and we will use the length parameter to cancel out other length dimensions for other parameters. And finally, we just check if the final parameters is the dimensionless parameter. So this is just one example. We just consider the body forms behaviors. So first, as I mentioned, if we do the model testing for body forms, so how many variables will involve in our practical phenomena? So for these problems, we will have the velocity, and we will have the gravity, and we will have the falling height, edge. So we have three variable, right? And we just list the how many basic dimensions are involved. So as the velocity, the dimension is L divided T, right? And the gravity is the acceleration, so the dimension is L divided T squared, and the falling height is the L. So actually we have two basic dimension. So the 3 minus 2 is 1. So we only have the one pi groups. Okay, so as we after we list all of the dimension for our physical variables, and then we just use the h to cancel out L parameters for other uh, physical variables. So for the velocity, we need to divide the h, and then you see the L dimension is cancelled out. And for the gravity, we need to also divide the h, and you see the L length is cancelled out. We only have the t squared over 1 for gravity and the t over 1 for velocity. And then we just use the G gravity divided the h ratio to cancel out the t dimensional. So finally, we have the V divided the root of the GH, and there is no dimensions involved in these physical properties. So we call it as uh, dimensionless parameter. And for these questions, we only have the one pi group, so there's only one pi group. So the pi involved in this problem is the V divided the root of the GH. And after the dimensional analysis, we only know that the, the pi, only one pi group, and this is equal to the constant values. But we didn't know the constant coefficient after we do the dimensional analysis. But based on the physical ideas, we know that for these problems, we need to satisfy the energy balance, right? So we have the kinematic energies need to equal to the potential energies. So based on these uh, uh, basic ideas, we know that the 2 over 1 mass v squares is the kinematic energy need to equal to the potential energies mgh. So we know that also make reorganize the equations, and we know the v squared and divided the gh is equal to 2. So you compute the root. So the v divided the gh root is equal to root 2. So based on the physical ideas, we can directly to compute the constant coefficients for these problems. So we directly know that the coefficient is 2. But if we didn't know the basic ideas for the energy balance, it seems that this is a simple way we can conduct the laboratory experiment. We just measure the Boeing velocities, and we just drop our ball with a different height, and then we can uh, measures have a different laboratories data points, and then we do the regression line, and the slope of a regression line indicate the constant coefficients. Okay. So after we do the dimensional analysis, and we can pick out the pi groups. For this example, our pi group is the v velocity divided the root of the gh. So this is the dimensional these parameters. So we can based on these parameters to conduct the laboratory experiments to understand and figure out how large of the constant coefficient. Okay, so uh, the second examples is related to the jack force we have mentioned before, and this is try to understand the jack force Fd of the spheres in a fluid flowing past the sphere is a function of the viscosity mu, and the mass density rho, and the velocity of the flow v, and the diameter the d. So this is again we just follow step by step dimensional analysis. So we just see how many numbers of the physical parameters we have. It's 5 because we have the jack force, velocity, density, mu, viscosity, and the d diameters, and how the numbers of the dimensions is the d. So for these problems, we use the 5 minus the 3 is equal to 2. So actually we have the 2 pi groups. We have the 2 pi groups. So if you follow the step by step, you can find out the, the, the pi groups. Okay, so as you see, because of the time limit, because today we still have the pipe quiz, so I just quickly introduce, and on the Friday I will provide more details. So you see that this is the final answers. We know that the jack force divided the low v square, and the d square is a function of the mu divided the low vd. So this is the Reynolds numbers related to the Reynolds numbers. As I mentioned, the Reynolds number is equal divided to the low VD divided the viscosity, which can be used to describe the flow conditions is laminar flow or the turbulent flow. And the left hand side, this is very famous coefficient. We call that is the drag force coefficient. The drag force coefficient. And the two are very famous dimensionless parameters. Okay, so next class I will introduce more details. Okay, so now due to the time limitations, so we just move to show off the quiz. As you see, today we only have the one quiz. The quiz only for one questions, and the figure showing here is from the textbook. Okay, so I will introduce the quiz by Mandarin. 所以可以看到今天我们只有一个题目。那第一题我们有两个小题 ，A 小题，我们可以从图中看到有两条线，一条是EGL，一条是 HGL。那我们可以看到这个能量迫降线跟这个水力动迫降线它们是直线跟虚线是有差异存在的。所以我们第一件事情希望这是两个 tank， 然后中间我们连接了一个 pipe。那在这样的条件下，它的水力迫降线是绘制成这样子。那第一个问题是，请你定义什么叫做 HGL， 什么叫做 EGL。那这个占了40分。然后第二小题，假想我们的水头损失，这个 head loss 在这个 pipe 里面，你可以把它定义成这个 HL 等于 0.03 乘上 L 除上 D，再乘上 V 的平方除上2G。所以你知道我们 L 如果越长的话，损失越大 ；D 越小的话，损失也越大。在这个管子中的流速越大的话，损失也会越大。那我们只知道这个平均速度是 V， 然后管径我们用这个 D 做描述，然后 L 是 pipe 的长度。那这个问题里面，其实我们有两个不一样管径的 pipe， 然后也拥有不一样的长度。所以我们可以看到，它告诉你说，上游的管子跟下游的管子分别是150米跟60米。那它们的管壁的直径，更正一下，这是说上游的这个水位高层跟下游的这个水位高层是150米跟60米。那管壁的这个长度跟直径是在这里。跟你讲，上游的管壁的直径比较大，它是32公分，然后它的长度比较长，它有190公尺。那下游的管壁的直径比较窄，是12公分，那它的长度有110公尺。那我们假设 gravity 是9.81， 然后这个动量修正的这个系数阿尔法是1，请你决定在这个系统里面的 Q， 也就是说的流量有多大。那显然我们这个必须要用到能量方程跟连续方程来去思考这个问题。